Imagine a galaxy whose light has been traveling for 13.5 billion years, warped by the gravity of a massive cluster into a cosmic mirage, revealing structures formed mere hundreds of millions of years after the Big Bang. This isn't just a snapshot of the universe's infancy, it's a lens forged by Einstein's theory of general relativity, bending spacetime itself to act as a natural telescope. The James Webb Space Telescope captures these distorted light paths, unraveling secrets from a time when the cosmos was still a toddler, its first stars flickering to life. What we see isn't just distant, it's a ghostly echo of the universe's earliest moments, stretched and magnified by the gravity of intervening galaxies. These images, rendered in infrared, show galaxies so far away their light has been stretched into redder wavelengths, revealing a time when the universe was less than 500 million years old. It's as if we're peering through a cosmic kaleidoscope, each shard of light a story of star formation, dark matter, and the universe's relentless expansion, proof that Einstein's predictions, once considered pure math, now guide us to the edges of the known universe. In this chapter, we uncover a groundbreaking discovery made possible by the James Webb Space Telescope, which has leveraged a prediction from Albert Einstein's theory of general relativity to peer deeper into the universe than ever before. At the heart of this achievement is a phenomenon known as gravitational lensing, a concept that Einstein himself foresaw a century ago. By harnessing this effect, the Webb telescope has revealed galaxies so distant that their light has been traveling for over 13 billion years, offering a glimpse into the universe's earliest moments. But how does this work, and why is it revolutionary? Let's break it down. Einstein's theory of general relativity, published in 1915, describes gravity not as a force but as the curvature of spacetime caused by massive objects. This curvature can bend the path of light, much like a glass lens refracts light. In 1930, Einstein himself proposed that this effect could magnify distant objects, a prediction that remained theoretical for decades. It wasn't until the 1980s that astronomers confirmed gravitational lensing by observing how light from distant galaxies was distorted by the gravity of massive foreground objects, like galaxy clusters. Now, the James Webb Telescope is using this same principle to amplify the light of galaxies so far away that their light has been traveling for over 13 billion years, long before the first stars and galaxies formed. This is not just a technical feat, it's a window into the universe's infancy. The Webb telescope, launched in 2021, is uniquely suited to this task. Its primary mirror, 6.5 meters in diameter, is the largest ever deployed in space, allowing it to collect more light than its predecessor, a Hubble Space Telescope. However, its true power lies in its advanced instruments, particularly the near-infrared camera, NIRCam, and the mid-infrared instrument, MIRI, which can detect the faint, redshifted light from ancient galaxies. These instruments are optimized for infrared wavelengths, which are crucial because the expansion of the universe has stretched the light from distant objects into the infrared spectrum. Without this capability, the faintest galaxies would remain invisible. Gravitational lensing acts as a cosmic magnifying glass. When light from a distant galaxy passes near a massive object, such as a galaxy cluster, the gravity of that object bends the light, creating multiple images, arcs, or even brightened regions of the distant galaxy. This effect can amplify the light by factors of tens or even hundreds, making it possible to observe galaxies that would otherwise be too faint to detect. The Webb telescope has identified several such lensed galaxies, some of which are over 13 billion light-years away. These galaxies are so distant that their light has been traveling for nearly the entire age of the universe, providing a rare opportunity to study the conditions of the early cosmos. One of the most striking discoveries involves a galaxy named GNZ11, which was previously the farthest known object in the universe. However, the Webb telescope has now identified galaxies that are even farther, with redshifts exceeding 13. These galaxies are so distant that they existed just 300 million years after the Big Bang. Their light has been stretched into the infrared, making them visible only with the Webb's advanced instruments. By analyzing these galaxies, scientists are gaining insights into the formation of the first stars and galaxies, a period known as the cosmic dawn. This era is critical because it marks the transition from a dark, featureless universe to one filled with light and structure. The significance of these findings extends beyond simply seeing farther. The galaxies observed by the Webb telescope are also helping scientists understand the distribution of dark matter, an invisible substance that makes up most of the universe's mass. Galaxy clusters, which act as natural lenses, are particularly useful for studying dark matter because their gravitational pull can bend light in ways that reveal the presence of unseen mass. By mapping how light is distorted around these clusters, astronomers can infer the distribution of dark matter and test theories about its nature. This connection between gravitational lensing and dark matter highlights the telescope's role in addressing one of the greatest mysteries in astrophysics. Another key aspect of these discoveries is the ability to study the earliest galaxies in unprecedented detail. The Webb telescope's high resolution allows scientists to resolve features within these distant galaxies, such as their star-forming regions and the distribution of gas and dust. This level of detail is crucial for understanding how galaxies evolved over time. For example, the discovery of galaxies with unusually high rates of star formation suggests that the early universe may have been more active than previously thought. These findings challenge existing models of galaxy formation and could lead to new theories about the processes that shape the cosmos. The use of gravitational lensing also raises intriguing questions about the nature of the universe itself. By observing how light is bent by massive objects, scientists can test the predictions of general relativity on a cosmic scale. These tests are essential for verifying the theory's validity in extreme conditions, such as those found in the vicinity of supermassive black holes or galaxy clusters. Additionally, the study of lensed galaxies provides a way to measure the expansion rate of the universe, a key factor in understanding its ultimate fate. These measurements are particularly important as they help distinguish between different cosmological models, including those that incorporate dark energy and dark matter. The implications of these discoveries are far-reaching. By peering into the distant past, the James Webb Telescope is not just expanding our view of the universe, it's reshaping our understanding of its origins and evolution. The galaxies observed through gravitational lensing offer a unique opportunity to study the universe's earliest moments, providing clues about the formation of the first stars, the assembly of galaxies, and the role of dark matter in shaping cosmic structures. These insights are critical for building a comprehensive picture of the universe's history and its future trajectory. As we continue to analyze the data from the Webb telescope, we can expect more revelations about the cosmos. The combination of advanced technology and Einstein's pioneering theory of relativity has opened a new frontier in astronomy, allowing us to explore regions of the universe that were once thought to be beyond our reach. The discoveries made so far are just the beginning, and they underscore the power of scientific curiosity and innovation in unraveling the mysteries of the universe. In the coming years, the Webb telescope will undoubtedly continue to push the boundaries of our knowledge, bringing us closer to answering some of the most profound questions about our place in the cosmos. The James Webb Space Telescope, launched in December 2021, is a marvel of engineering and a testament to humanity's relentless pursuit of understanding the cosmos. Its mission is not just to capture images of distant galaxies but to probe the very edges of the universe, where the light from the earliest stars and galaxies has traveled billions of years to reach us. To achieve this, scientists have turned to a phenomenon predicted by Albert Einstein over a century ago: gravitational lensing. This effect, a consequence of Einstein's theory of general relativity, allows massive objects like galaxies and galaxy clusters to act as cosmic lenses, bending and magnifying the light from objects behind them. By harnessing this natural phenomenon, the James Webb Telescope has unlocked a new way to peer into the universe's infancy, revealing galaxies that formed just hundreds of millions of years after the Big Bang. But how did scientists arrive at this groundbreaking method, and what tools and techniques made it possible? Let's trace the journey from Einstein's theory to the telescope's first breathtaking images of the cosmos. Einstein's theory of general relativity, published in 1915, revolutionized our understanding of gravity. Unlike Newton's view of gravity as a force acting at a distance, Einstein described it as the curvature of spacetime caused by mass. This curvature affects not just the motion of objects but also the path of light. When light passes near a massive object, it bends, creating a phenomenon known as gravitational lensing. For decades, this prediction remained theoretical, but in the 1930s, astronomers began to observe its effects. The first confirmed instance came in 1919, when observations of starlight bending around the Sun during a solar eclipse provided empirical evidence for Einstein's theory. Since then, gravitational lensing has become a powerful tool in astrophysics, allowing scientists to study distant objects that would otherwise be invisible. The James Webb Telescope's design was built with this concept in mind. Unlike its predecessor, the Hubble Space Telescope, which operates primarily in the visible and ultraviolet spectrum, Webb is optimized for infrared light. This is crucial because the light from the earliest galaxies has been stretched over billions of years, shifting into the infrared part of the spectrum. To capture this faint, redshifted light, Webb's instruments are engineered to detect infrared wavelengths with unprecedented sensitivity. Among its key tools is the near-infrared camera, NIRCam, which uses advanced detectors to capture images of distant galaxies. Another vital instrument is the mid-infrared instrument, MIRI, which can detect even fainter signals, enabling scientists to study the faintest and most distant objects. But how does gravitational lensing play into this? Imagine a massive galaxy cluster acting as a natural lens, bending the light from a distant galaxy behind it. This effect magnifies the light, making the distant galaxy appear brighter and larger than it would otherwise be. For scientists, this is a double-edged sword. It allows them to see objects that would be otherwise too faint to detect, but it also introduces complexities in interpreting the data. The light from these distant galaxies is distorted, creating arcs and brightened regions that require careful analysis to untangle. The James Webb Telescope's instruments are designed to capture these subtle distortions, providing clues about the distribution of mass in the lensing objects and the properties of the distant galaxies themselves. The process of using gravitational lensing to study the early universe is both intricate and collaborative. Scientists begin by identifying potential lensing systems, galaxy clusters that are known to bend light. These clusters are often located in the foreground of the universe, with the distant galaxies they magnify situated billions of light-years away. Once a candidate system is identified, the telescope's instruments are directed at it, capturing detailed images and spectra. The data collected is then analyzed using sophisticated algorithms and models to account for the lensing effects. This involves reconstructing the original shape and light distribution of the distant galaxy, a process that requires immense computational power and careful calibration. One of the most significant challenges in this endeavor is the sheer distance of the objects being observed. The light from these galaxies has traveled for over 13 billion years to reach us, meaning we are seeing them as they were in the early universe. The faintness of this light, combined with the distortions caused by gravitational lensing, makes the data analysis particularly complex. Scientists must account for factors such as the distribution of dark matter within the lensing galaxy clusters, which can further complicate the interpretation of the images. Despite these challenges, the James Webb Telescope's advanced instruments and the collaborative efforts of scientists around the world have made it possible to overcome these obstacles. The timeline of the James Webb Telescope's mission has been marked by milestones that highlight the intersection of theory and observation. After its launch in December 2021, the telescope embarked on a journey to its operational orbit, a point known as the second Lagrange point, L2, approximately 1.5 million kilometers from Earth. This location provides a stable environment for the telescope, minimizing the interference of Earth's atmosphere and allowing for continuous observation. By July 2022, the telescope had completed its commissioning phase, during which its instruments were calibrated and tested. The first images released in that month showcased the telescope's capabilities, including the famous image of the galaxy cluster Abell 2744, where gravitational lensing revealed thousands of background galaxies. Since then, the telescope has continued to deliver groundbreaking results. One of its most notable achievements has been the observation of galaxies formed just a few 100 million years after the Big Bang. These galaxies, which are among the oldest and most distant ever detected, provide critical insights into the early stages of galaxy formation and the evolution of the universe. The data collected by Webb has also helped scientists refine their understanding of dark matter and the distribution of mass in galaxy clusters, further validating the predictions of Einstein's theory. The significance of these findings extends beyond the technical achievements of the telescope. They represent a profound leap in our understanding of the universe's history and its fundamental processes. By observing the earliest galaxies, scientists can study how stars and galaxies formed, how they evolved, and how they contributed to the large-scale structure of the cosmos. These observations also offer a glimpse into the conditions of the early universe, shedding light on the mysterious forces that shaped it. The James Webb Telescope's ability to harness gravitational lensing has thus become a cornerstone of modern astrophysics, bridging the gap between theoretical predictions and observational evidence. As the James Webb Telescope continues its mission, it stands as a symbol of human ingenuity and the power of scientific collaboration. The journey from Einstein's theoretical prediction to the telescope's ability to capture images of the universe's infancy is a testament to the enduring quest for knowledge. Each image and dataset collected by Webb not only advances our understanding of the cosmos but also reminds us of the profound questions that remain. How did the universe begin? What forces shaped its evolution? And what lies beyond the farthest reaches of space? The answers, waiting to be discovered, are as vast and mysterious as the universe itself. The James Webb Space Telescope's ability to peer into the farthest reaches of the universe hinges on one of the most profound predictions in modern physics, Einstein's theory of general relativity. This theory, formulated in 1915, revolutionized our understanding of gravity by describing it not as a force but as the curvature of spacetime itself. Massive objects like stars, galaxies, and even black holes warp the fabric of space, bending the path of light that passes near them. This effect, known as gravitational lensing, is the key to unlocking the secrets of the cosmos that the Webb telescope is now revealing. But how does this ancient prediction, born from Einstein's equations, enable us to see galaxies that formed just a few 100 million years after the Big Bang? Let's unravel the science behind this extraordinary achievement. Imagine holding a magnifying glass over a distant object. The glass bends light, making the object appear larger and brighter. On a cosmic scale, galaxies act as natural magnifying glasses, distorting and amplifying the light from even more distant objects behind them. This phenomenon, gravitational lensing, is not just a visual trick, it's a powerful tool for astronomers. When light from a distant galaxy passes near a massive foreground object, such as a cluster of galaxies, the light bends around it, creating distorted, stretched, or even multiple images of the background galaxy. These distortions can magnify the light, making faint objects visible that would otherwise be lost in the darkness of space. For the James Webb Telescope, this effect is a lifeline. The light from the earliest galaxies has been traveling for over 13 billion years, stretching into the infrared spectrum. Without gravitational lensing, these galaxies would be too faint to detect, even with Webb's advanced instruments. By harnessing this cosmic magnification, scientists can peer back in time to the universe's infancy, when the first stars and galaxies were born. But why is this significant? The universe we see today is a vast, intricate web of galaxies, dark matter, and dark energy, but its origins remain shrouded in mystery. The earliest galaxies formed in the first few 100 million years after the Big Bang, a period known as the Cosmic Dawn. These primordial galaxies were small, irregular, and dense, yet they laid the foundation for the structures we observe today. However, studying them is like trying to glimpse a candle flame from across a dark room. Without the right tools, they are invisible. Gravitational lensing acts as a cosmic flashlight, bending and amplifying the light from these distant objects, allowing us to see them in exquisite detail. This is where the James Webb Telescope's mission becomes transformative. By combining its infrared sensitivity with the power of gravitational lensing, scientists can map the distribution of matter in the early universe, trace the formation of the first galaxies, and even detect the faint signatures of the first stars. These observations are not just about seeing further, they're about understanding how the universe evolved from a chaotic, dense state into the structured cosmos we inhabit today. The significance of gravitational lensing extends beyond mere visibility. It also provides a way to measure the mass of dark matter, an invisible substance that makes up most of the universe's mass but does not emit or absorb light. Dark matter's gravitational pull shapes the large-scale structure of the cosmos, yet its nature remains one of the greatest mysteries in physics. Gravitational lensing allows astronomers to map the distribution of dark matter by observing how it bends light from distant galaxies. The distortions caused by dark matter can be detected even when no visible matter is present, offering a glimpse into the invisible scaffolding that holds the universe together. For the James Webb Telescope, this means it can not only observe distant galaxies but also study the unseen forces that govern their formation and evolution. This dual capability, seeing both the light and the dark, makes the telescope a unique instrument for probing the universe's most fundamental questions. However, gravitational lensing is not a passive process. It requires precise alignment between the distant galaxy, the massive foreground object, and the observer. The chance alignment of these three elements is rare, making each instance of lensing a valuable opportunity for discovery. The James Webb Telescope's ability to detect these rare alignments is a testament to its advanced technology and the power of Einstein's theory. By capturing images of galaxies that are magnified and distorted by gravitational lensing, scientists can study the properties of these distant objects in ways that would be impossible otherwise. For example, the light from a galaxy that is billions of light-years away can be stretched into an arc or multiple images, allowing researchers to measure its mass, composition, and even the rate at which it is forming new stars. These observations provide critical insights into the conditions of the early universe, such as the density of matter, the distribution of dark matter, and the role of cosmic inflation in shaping the cosmos. The implications of these discoveries are profound. By studying the earliest galaxies, scientists can test theories about how the first stars formed, how they influenced the formation of galaxies, and how the universe transitioned from a hot, dense state to the structured universe we see today. These galaxies are not just relics of the past, they are the building blocks of the cosmos. Understanding their formation and evolution helps us piece together the timeline of cosmic history, from the Big Bang to the present day. Moreover, the data collected by the James Webb Telescope can refine our models of dark matter and dark energy, two mysterious components that make up the majority of the universe's mass-energy content. By observing how gravitational lensing affects the light from distant galaxies, researchers can infer the distribution of dark matter and how it interacts with visible matter. This, in turn, helps us better understand the forces that are shaping the universe's future, including its ultimate fate, whether it will continue to expand indefinitely or eventually collapse under its own gravity. The connection between Einstein's theory and the James Webb Telescope's mission is a beautiful example of how fundamental physics can drive astronomical discovery. Einstein's equations predicted that gravity would bend light, a phenomenon that was first confirmed during a solar eclipse in 1919. Since then, gravitational lensing has become a cornerstone of modern astrophysics, enabling scientists to study distant objects, map dark matter, and even detect exoplanets. The James Webb Telescope builds on this legacy by pushing the boundaries of what is possible. Its infrared capabilities allow it to detect light that has been stretched into the infrared spectrum by the expansion of the universe, while gravitational lensing provides the additional magnification needed to see the faintest objects. Together, these tools create a powerful synergy, allowing astronomers to explore regions of the universe that were previously inaccessible. But the significance of this work goes beyond the technical achievements of the telescope. It also speaks to the human drive to understand our place in the cosmos. The James Webb Telescope is not just an instrument, it is a bridge between the present and the distant past, a way to peer into the origins of the universe and ask questions that have puzzled scientists for centuries. By using Einstein's predictions to observe the farthest reaches of space, we are not only expanding our knowledge of the cosmos, we are also reaffirming the power of human curiosity and ingenuity. Each image captured by the telescope is a testament to the enduring relevance of Einstein's theory and the remarkable progress of modern astronomy. As we continue to analyze the data from the James Webb Telescope, we are uncovering new layers of complexity in the universe, challenging existing theories, and opening up new avenues of research. This is the essence of scientific exploration, to look beyond what we know, to seek answers in the unknown, and to find that the universe is far more intricate and fascinating than we ever imagined. In the early 20th century, humanity's understanding of the cosmos was still shaped by the laws of Newtonian physics. But a revolutionary idea was about to change everything. In 1915, Albert Einstein published his theory of general relativity, a framework that redefined gravity as the curvature of spacetime itself. This theory predicted something astonishing: light, which had always been thought to travel in straight lines, would bend when passing near massive objects. At the time, this was a radical concept, but Einstein's equations suggested that the gravity of a star could warp the fabric of space, causing light to curve around it. This idea was initially met with skepticism, but it would soon be tested in a way that would cement Einstein's legacy and lay the groundwork for modern astrophysics. The first major confirmation came in 1919, during a solar eclipse. Astronomers observed starlight bending around the sun, exactly as Einstein's equations predicted. This moment marked a turning point, proving that spacetime could be distorted by mass and that light could be influenced by gravity in ways previously unimaginable. But Einstein's theory was more than just a mathematical curiosity, it opened the door to new ways of observing the universe. For instance, it introduced the concept of gravitational lensing, where the gravity of a massive object could act like a cosmic magnifying glass, bending and amplifying the light from distant sources. This phenomenon would become a cornerstone of modern astronomy, especially in the quest to peer into the farthest reaches of space. However, it would take decades for scientists to fully harness these ideas. The early days of space exploration in the 1960s and 1970s were dominated by missions that relied on visible light and ultraviolet wavelengths. Telescopes like the Hubble Space Telescope, launched in 1990, revolutionized our view of the universe by capturing images of distant galaxies and nebulae. But even with Hubble's capabilities, there were limits. The universe is filled with dust and gas that absorb visible light, obscuring some of the earliest stars and galaxies. To see beyond these barriers, astronomers needed to look in a different part of the electromagnetic spectrum, specifically, the infrared. Infrared light, which is invisible to the human eye, can penetrate cosmic dust and reveal the glow of ancient stars and galaxies. This shift in wavelength also meant that light from the earliest objects in the universe would have been stretched over time due to the expansion of the universe, a phenomenon known as redshift. The longer the distance, the more the light is stretched, making it appear in the infrared range. This connection between redshift and infrared observation became a key insight, but it wasn't until the late 20th century that technology advanced enough to make infrared astronomy practical. The Infrared Astronomical Satellite, IRAS, launched in 1983, was one of the first missions to systematically map the infrared sky. It discovered thousands of previously unseen objects, including distant galaxies and star-forming regions. However, IRAS and its successors were limited by their size and the technology of the time. The need for a more powerful infrared telescope became apparent, especially as astronomers began to realize that the universe's earliest galaxies, formed just a few 100 million years after the Big Bang, might be hidden behind cosmic dust. The James Webb Space Telescope, launched in 2021, was designed to overcome these challenges. Its massive mirror, nearly 3 times larger than Hubble's, allows it to collect more light and detect fainter, more distant objects. But Webb's capabilities go beyond just size. Its ability to observe in the infrared spectrum is a direct application of Einstein's predictions, particularly gravitational lensing. By combining the bending of light predicted by general relativity with the power of infrared observation, Webb can peer into regions of the universe that were previously inaccessible. 4. Example: gravitational lensing allows Webb to magnify the light from distant galaxies, making them visible even when they are billions of light-years away. This technique has been used for decades, but Webb's advanced instruments and sensitivity take it to a new level. The first images released by Webb in 2022 showcased galaxies that existed just 300 million years after the Big Bang, a time when the universe was still young and its structure was taking shape. These discoveries were made possible by the interplay between Einstein's theory and modern technology. But the journey to this point was long and complex. The idea of using gravitational lensing to study distant objects dates back to the 1930s, when Einstein himself speculated about its potential. In the 1970s and 1980s, astronomers began to observe lensing effects in galaxy clusters, where the combined gravity of thousands of galaxies acted as a natural telescope. These observations confirmed Einstein's predictions and demonstrated the power of lensing as a tool for astronomy. However, the full potential of this technique remained unrealized until the development of space-based telescopes like Hubble and Spitzer. The Spitzer Space Telescope, launched in 2003, was the first to operate primarily in the infrared range, allowing it to study the early universe in ways that visible light telescopes could not. Spitzer's discoveries laid the foundation for Webb's mission, revealing the existence of galaxies that were too faint and distant to be observed with earlier instruments. Yet, even Spitzer had limitations. Its smaller mirror and shorter operational lifespan meant it could only capture a fraction of the data that Webb could provide. The James Webb Space Telescope was designed to push these boundaries further. Its advanced infrared sensors, combined with the ability to detect faint light, make it uniquely suited to study the earliest galaxies and the formation of the first stars. But Webb's capabilities are not just about size and sensitivity, they are also about the application of Einstein's theories in ways that were once theoretical. Gravitational lensing, for instance, is not just a tool for magnifying distant objects, it also provides insights into the distribution of dark matter, which is thought to make up most of the universe's mass. By analyzing how light is bent around galaxy clusters, scientists can map the gravitational effects of dark matter and test the predictions of general relativity on a cosmic scale. This connection between Einstein's theory and modern astrophysics is a testament to the enduring power of his ideas. The James Webb Space Telescope is not just a technological marvel, it is a bridge between the theoretical insights of the early 20th century and the observational capabilities of the 21st. Its ability to probe the farthest reaches of the universe is a direct result of decades of scientific progress, from the confirmation of Einstein's predictions to the development of infrared astronomy. Each step along the way was driven by curiosity and the desire to understand the cosmos in ways that were once thought impossible. Today, as Webb captures images of galaxies that existed just a few 100 million years after the Big Bang, it is a reminder of how far our understanding has come and how much further we have to go. The journey from Einstein's equations to the James Webb Space Telescope is a story of human ingenuity, perseverance, and the relentless pursuit of knowledge. It is a story that continues to unfold, with each new discovery bringing us closer to the mysteries of the universe. As we look deeper into the cosmos, the James Webb Telescope reveals not just the beauty of distant galaxies but also profound questions about the universe's origins and structure. At the heart of its mission lies a prediction made over a century ago by Albert Einstein: the bending of light by gravity. This phenomenon, known as gravitational lensing, has become a cornerstone of modern astrophysics. But while the telescope's ability to harness this effect to peer into the farthest reaches of the universe is awe-inspiring, it also opens the door to mysteries that challenge our understanding of physics. What exactly does this lensing effect tell us about the universe's hidden architecture? And how do scientists reconcile the data with existing theories? These are the open questions that drive the current scientific debate. For instance, gravitational lensing allows us to magnify distant objects, but interpreting the resulting images is far from straightforward. The light we see might be distorted in ways that obscure the true nature of the objects themselves. Are we witnessing the actual structure of galaxies, or are we seeing a distorted reflection of their light? This ambiguity has sparked intense discussions among researchers, who are working to refine models that can distinguish between these possibilities. Moreover, the telescope's observations have uncovered galaxies that existed just a few 100 million years after the Big Bang. These ancient systems challenge our understanding of how galaxies form and evolve. Yet, their existence raises new questions. What conditions allowed such massive structures to form so early in the universe's history? Could dark matter have played a role in accelerating their growth? While dark matter remains a leading hypothesis, its exact nature remains elusive. The James Webb Telescope's data may provide clues, but it also highlights the gaps in our knowledge. For example, the telescope's infrared capabilities allow it to peer through cosmic dust, revealing previously hidden regions of the universe. However, the same dust can obscure our view, creating a paradox where the very obstacles to observation become sources of discovery. Scientists are now grappling with how to navigate these challenges, using advanced computational models to simulate the universe's early stages and compare them with observations. Yet, even with these tools, there are limits. The telescope's instruments, while revolutionary, have constraints in resolution and sensitivity. This means some phenomena, such as the precise distribution of dark matter or the dynamics of the first stars, may remain beyond our current reach. Furthermore, the sheer scale of the data collected by the telescope has outpaced our ability to analyze it fully. Researchers are now facing the daunting task of sifting through vast datasets to identify patterns that could reshape our understanding of cosmic evolution. This process is not without controversy. Different teams may interpret the same data through varying lenses, leading to debates over what the observations truly signify. For instance, some argue that the observed lensing effects could be explained by alternative theories of gravity, challenging the need for dark matter altogether. These discussions underscore the dynamic nature of scientific inquiry, where each discovery opens new avenues of exploration. The James Webb Telescope's mission is not just about answering existing questions but about redefining the boundaries of what we know. As scientists continue to analyze its findings, they are also setting the stage for future missions that will build on these insights. Yet, for all its advancements, the telescope cannot resolve every mystery. The universe, in its vastness, still holds secrets that defy even the most sophisticated instruments. And that, perhaps, is what makes the journey of discovery so compelling. Each observation is a step toward understanding, but also a reminder of how much remains unknown. The questions raised by the James Webb Telescope are not just scientific, they are philosophical. They force us to confront the limits of our knowledge and the humility required to seek answers in a universe that continues to surprise us. As we move forward, the interplay between observation, theory, and curiosity will remain central to unraveling the cosmos' deepest enigmas. James Webb Telescope uses trippy Einstein prediction to probe the farthest reaches of the universe. Space photo of the week. This part of our deep dive into James Webb Telescope uses trippy Einstein prediction to probe the farthest reaches of the universe. Space photo of the week focuses on explain what's coming next, future missions, instruments, or observations that could confirm, extend, or challenge what we know so far. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. So, what did we just uncover about the James Webb Space Telescope and its cosmic detective work? Let me break it down. First, the telescope isn't just a camera in space, it's a time machine, powered by one of Einstein's most mind-bending predictions, that massive objects can warp spacetime itself. This effect, called gravitational lensing, acts like a cosmic magnifying glass, bending light from distant galaxies around massive structures like galaxy clusters. By studying these distorted shapes, Webb can peer back billions of years, capturing light from galaxies that formed just hundreds of millions of years after the Big Bang. It's like looking at the universe's baby pictures, but with a twist. Those images are warped, stretched, and sometimes even split into multiple arcs, creating the so-called trippy visuals that have captivated astronomers and the public alike. These distortions aren't just pretty patterns, they're clues. They help scientists measure the distribution of dark matter, which shapes the universe's structure, and track how galaxies evolved in the early cosmos. But here's the kicker: Webb's ability to detect these faint, distant galaxies relies on Einstein's equations, which predicted this lensing effect over a century ago. It's a testament to how foundational physics theories can guide modern exploration, bridging the gap between Einstein's 1915 equations and today's cutting-edge observatories. And then there's the sheer scale of what we're seeing. The galaxies Webb observes are so far away that their light has been traveling for over 13 billion years to reach us. By studying their light, scientists can analyze the composition of these ancient systems, revealing how stars formed in the earliest epochs of the universe. This isn't just about pretty pictures, it's about answering fundamental questions. How did the first galaxies assemble? What role did dark matter play in their formation? And how did the universe transition from a chaotic, dense state to the structured cosmos we see today? The Webb telescope's images, with their eerie, glowing arcs and shimmering halos, are more than aesthetic marvels. They're data-rich snapshots of the universe's infancy, offering insights into the processes that shaped the cosmos. Yet, there's still so much to learn. The lensing effects Webb captures are also helping map the invisible scaffolding of the universe, dark matter's gravitational influence, allowing researchers to test theories about the universe's ultimate fate. And as Webb continues its mission, it's likely to uncover even more surprises, perhaps even galaxies that predate the cosmic dark ages, rewriting our understanding of the universe's earliest moments. So, what does this mean for us? It means that the tools we build today, rooted in centuries-old physics, can still unlock secrets from the universe's distant past. It's a reminder that science is a conversation across time, where the equations of the past illuminate the mysteries of the present. And for those of you wondering what's next, the journey isn't over. The James Webb Space Telescope is just one chapter in humanity's quest to understand the cosmos. If you want to stay in the loop, hit that subscribe button and join us every week for more deep dives into the wonders of space. And if you've got a question, a theory, or just want to share your thoughts, drop a comment below. After all, the universe is full of mysteries, and every question we ask brings us closer to the answers.